Hi, my name is Abhishek. I am Strategic Customer Relationship Manager for Talend. Talend has been popularly known for its open source integration software that allows you to easily create data pipelines. Starting in 2005, we have evolved as a company known for best in class data integration software, from big data to cloud integrations. In this talk, let me take you through a journey to appreciate the shift in mindset of looking at data processing pipelines. We will first talk about a paradigm shift, that is, how the patterns of programming in this space are changing. Then we will talk about the notion of unified data pipeline, which will lead us to talk about Apache Beam and a Talend product which is built on top of it. So let's set the perspective that will help guide your thinking as we proceed. The data people, all of you have a problem, a real problem that needs to be solved with help of data. It doesn't matter whether it's small or big data. Data is most of the time just an enabler for the innovation that you're looking for. Bulk of that problem solving usually starts with spreadsheets, right? And you can't get away with them easily. They're all everywhere. And you soon hit a challenge where the scale of data becomes part of the problem, where you start to call it the big data. And then you realize that you can only be as fast as the capacity on your laptop. So what do? You write code and learn new frameworks to solve your problems. But then programming takes ages to master. Let's take an example which is generic enough for you to relate to your business. Let's say you work at a mobile gaming company. You have millions of users generating billions of data points, and you're trying to do simple user retention analysis by looking at the usage activity. If the data snapshot you're looking to analyze is just for one time, and if it fits a spreadsheet, you are likely to just compute and be done with it. But then you can't really operationalize it easily, so you pick up your coding skills to write code that gives you a bit more flexibility. But then the scale of data start to become your problem, and you start looking at the new skills to leverage parallel computing. And as soon as you want to do the calculations in real time, all the work you've been doing falls apart. You start to pick up new technologies and rewrite your piece of code for the streaming world. And in the process, you break your own code again and again, rewriting from one API to another. You see, at this point of time, you start looking at the complexities of distributed computing and low-level infrastructure. But what you really need to do is analyze and gain value from data. Scale without having to rewrite code. Implement new frameworks without having to rewrite your code. Avoid operational problems early on, and prevent having to learn several data processing frameworks. So what if we start to look at a programming model where as soon as you get down to write a piece of code, you don't worry about whether it's a small data or big data. Both should be the first class citizens. You don't want to worry about whether it's batch or real time. Write code that works both for batch scenarios as well as for stream processing. Future proof your code. No rewrite is needed. No need to learn new Spark API or a Flink API. And then make it scale proof, which is take it from your computer to your server farm without thinking too much about all the complexities of distributed systems. That's what Apache Beam is all about. So if you look at what is Apache Beam and how it evolved, you have to look at a history a little bit. MapReduce served as an interesting foundation for how people started thinking about large-scale big data processing. But then, since MapReduce, which came out of Google and the rest of the community came up with further improvements in the MapReduce model, and the open source community started building a lot of tools around the new models. So Thais became faster MapReduce, Spark came along for leveraging main memory. Apache Beam is trying to converge the innovation that happened in all the bits and pieces, and in retrospectively go back and look at what could be the next programming model after MapReduce. And that's what Beam model is all about. It's a generation beyond MapReduce. Apache Beam programming model uses a higher level of abstractions that let you focus on your application logic. You build a pipeline as an arbitrary graph that mixes custom element-wise processing with aggregations and library functions. Beam pipelines can process both bounded, which is fixed size data sets, as well as infinite streams of elements. And when you write your application logic, you don't need to worry which type of collection you'll be processing. This makes your pipeline and logic very flexible and reusable. Now, to truly unify batch and stream processing, we need to separate the notion of event time from processing time. Event time is the time an event happened. So for example, if you're processing scores from mobile gaming application, that would be the time when the user popped up balloons and crashed the candy or whatever they are doing. But that event time may differ from the time the element is processed, even in real-time system. This graph shows a sample data set of points scored for a specific team in our hypothetical mobile game application. On the x-axis, we've got event time, and the y-axis is the processing time. If everything was perfect, the elements would arrive in our system immediately, and so we would see things along this dashed line. But distributed systems often don't cooperate. Sometimes it's not too bad. So here's this event from just before 1207, maybe just encountered a small network delay and arrives almost immediately after 1207. But this one over here was more like 7 minutes late. Perhaps our user was playing in an elevator or something. So the score is delayed by a temporary lack of network activity. And the margins of this graph can't even contain what we would see if our game supports an offline mode. If the user was playing on a long flight in an airplane mode, it might be hours until that flight lands and we can get the scores for processing. These types of infinite out of order data sources can be really tricky to reason about unless you know what questions to ask. The Beam model is based on 4 key questions. What results are calculated? Are you doing computing sums, joins, histograms, machine learning models? Where in the event time are results calculated? Which is, how does the time each event originally occurred affect the result? The results aggregated for all time in fixed windows or as user activity sessions? When in the processing time are results materialized? Does the time each element arrives in the system affect the results? How do we know when to emit a result? What do we do about the data that comes in late from those pesky users playing on long flights? And finally, how do refinements relate? If we choose to emit results multiple times, is each result independent and distinct? Do they build upon one another? Let's take a quick look at how we can use these questions to build a pipeline. Here is a snippet from a pipeline that processes scoring results from that mobile gaming application. In orange, you can see the computation that we are performing, the what. In this case, we are taking team score pairs and summing them per team. So now let's see what happens to our sample data if we exclude this in traditional batch style. In this looping animation, the gray line represents processing time. As the pipeline executes and processes elements, they are accumulated into the intermediate state just under the processing timeline. When processing completes, the system emits the result in the yellow line. This is pretty standard batch processing. But let's see how answering the remaining three questions can make this more expressive. Let's start by playing with the event time. By specifying a windowing function, we can calculate independent results for different slices of event time. For example, every minute, every hour, or every day. In this case, we'll calculate an independent sum of every 2-minute window. Now if we look at how things execute, you can see that we are calculating an independent answer for every 2-minute period of the event time. But we are still waiting until the entire computation completes to emit any result. That might work fine for bounded data sets when we will eventually finish processing, but it's not going to work if we are to process an infinite amount of data. So what we need to do is to reduce the latency of an individual results. We do that by asking for results to be emitted or triggered based on the system's best estimate of when it has all the input data. We call this estimate the watermark. Now the graph contains the watermark drawn in the green, and by triggering at watermark, the result for each window is emitted as soon as we roughly think we are done seeing the data for that slice of time. But again, the watermark is often just a heuristic. It's the system's best guess about data completeness. Right now the watermark is too fast, and so in some cases we are moving without all the data, so that the user who scored 9 points in the elevator is just plain out of luck. Those 9 points don't get included in their team scores. But we don't want to be slow either. It's no good if we wait to emit until all the users have finished playing on long flights everywhere. So let's use more sophisticated trigger to request both speculative early firing as data is still trickling in, and also update the results if late elements arrive. Once we do this though, we might get multiple results for the same window of the event time. So we have answered the fourth question about how refined results relate. Here we choose to just continually accumulate the score. Now there are multiple results for each window. Some windows like the second produce early incomplete results as data arrives. There's one on time result per window when we think we have pretty much got all the data, and there are late results if additional data comes in behind the watermark, like the first window. So we started with an algorithm, what we wanted to compute. In this case, it happened to be a simple integer summation, just so that it would be reasonable to animate, but it could be much more complex computation. And Just by tweaking just a line here or there, we went through a number of use cases. From the simple traditional batch style through to an advanced streaming situation. Just like the MapReduce model fundamentally changed the way we do distributed processing by providing the right set of abstractions, we hope that this model will change the way we unify batch and stream processing in the future. So today, Apache Beam includes the core unified programming model revolving around the what, where, when, how questions, the SDKs for writing Beam pipelines, and the most important, portability, multiple runners that can execute Beam pipelines on existing distributed processing frameworks. So now, as you know about Beam, let me tell you what Talend offers for the Beam users. I call it Beam on steroids, and my team calls it data streams. It's a self-service data integration for everyone. Data streams allows you to get up and running with your data pipelines without even writing that Beam code. We further simplify the development of pipeline without you investing a lot of efforts in learning the Beam model. So what makes data streams so unique and easy to use? It comes with interactive live preview. So when you're building the pipeline, you'll actually see your data and its transformation in an interactive manner with sample data, which is pretty cool. It is schema-less by design, which is great for the design time and the runtime. Designers can create and refine pipeline more easily because the schema is dynamically discovered and the enforcement is optional. For runtime, pipelines are more resilient to schema changes. Obviously, because of Apache Beam, it supports the batch and the streaming. It works on multiple cloud, so it's very portable in that manner. And then it really truly allows you to extend the functionalities with code if you really want to write your own code in Python. And beyond that, you can even choose to run natively in the cloud platform where the data resides, truly achieving design once and run anywhere with any cloud across multiple cloud vendors. And obviously, it's part of a larger product suite that we offer. So it works very cohesively with everything else that we have to offer to our customers. So let's look at how data streams make it easy for you to build your pipeline. In a quick demo, I'm going to show you what it takes for you to spin up data streams. You can go to AWS Marketplace, and on AWS Marketplace, you just need to go and subscribe to the free data streams for AWS. It'll ask you a bunch of questions about what instance that you want to use, and although the software is free, you may have the infrastructure cost, so you'll select a specific AMI types which is cost efficient for your scenario, and go ahead and quickly launch your software. As soon as you launch, it will ask you for relevant instance details and configuration, the networking configuration and specific storage configuration. And once you're done with that, you are pretty much done. You have a running instance of Talend data streams. When you go to a public IP of your AWS instance, it'll take you to data streams web UI, which is protected by a username password. And as soon as you get in, you see a interface like this. There are three important elements in data streams. connections, data sets, and pipelines. You create a connection for accessing your source and target systems, which holds all the configuration related to access to your systems. You have all the important modern connectors that you need, and by the way, they all come from the Apache Beam community. So there are a bunch of them that they're available, and the community is actively building them. Once you have a connection, you go and create a data set from that connection. In my case, I have a custom data set over here, which is from an S3 bucket. It's all the aircraft data with their positions in the sky. And then you go and create a pipeline. When you create a pipeline, you see a canvas like this. You first start with creating a source. A source is a data set where you start with. In my case, I'm going to pick the aircraft's data set here. And as soon as you do that, you see a sample data below, and this is the area where it starts to get more interactive. So what you see here is the 50 sample records, which can be, you can see them raw, you can see them as a grid, and then once we select the input, which is your data set, you have to select the sink, which is your source, which is your target. I'm going to create a new data set over here called the aircraft output data set, and for now I'll use this as a CSV. And once you have the input and output, then you can start building your pipeline by selecting different processors. There are multiple processors, like for aggregation, for field selection. Let's have a quick look at the kind of data that we have. So I have a data set which has different flights with their operator, their latitude, longitude, and the ID of the aircraft. Maybe what we can do here is aggregate the data first by airline. We can aggregate all the flights by airline. For that, we will probably need an aggregate function. So let's pick that. So you see I have this right hand panel which opens up. For this aggregate processor, I can give a name, say group by airline, and then we've got to pick the column on which we have to aggregate it, in my case the operator, and then we can choose to figure out what elements we want to display and how. The operation that I'm trying to do over here is count, and then you can specify what the output field might look like. In my case, it can be number of flights per operator. And that's it. When you hit save on this, we can see the result in an interactive manner. You can click on the records and see what the output was. You can see that the input was 50 records and got reduced to 29 records. So this is giving you a quick feedback of what happened in that operation. And that's it. You can run the pipeline and see how it works. If you continue building the pipeline, it may look something similar to this, where we aggregate by aircrafts, we select the latest position, we can compute geohash, and then redirect it to whatever the output is. And that's it. This is how the entire pipeline looks like. You can execute it. In my case, I just have local Spark to execute it on, but in your case you may have Flink or anything else. This could be a real-time profile, or it could be a batch data, and when you trigger the execution, you can see all the logs here. And that's about it. This is data streams for you. Give it a try and let us know if you have any feedback. Thank you.